In this video, we're going to take a look at exam revision for variable acceleration. So what we're going to do here is just take a look at two exam style questions for variable acceleration. And as always, pause the video, have a look at the questions they appear, and double check that your solution matches what we get on the screen. Other than that though, I think that's everything that we need here to get started. So let's begin now with question 1. Starting off with question 1 then, where we have a particle P that moves along the x-axis. The displacement of the particle from the origin, x meters, t seconds after a given instant, is defined as the following equation here. And this is defined for t being greater than or equal to 0. So for this question here, we have to find the displacement of p when it is instantaneously at rest. Now we know that this particle p here will be instantaneously at rest when v equals 0. So in other words, when the velocity equals 0. So let's just make a note of that here. That is when v equals 0. So what we have here is the displacement, and we need the velocity to be equal to 0. So if we start with the displacement and we need the velocity, what we need to do then is differentiate the displacement here with respect to t. If you have the displacement and you want the velocity, then because we're moving down here, we need to differentiate. And the same would be true if you had the velocity and you wanted the acceleration. So to move down here, we differentiate, so that would be d by dt. Now it doesn't apply for this question here, there's no integration that's needed, but if you were going backwards then, so if you had the acceleration, for example, and you wanted the velocity, then you would need to integrate with respect to time, with respect to t. So going backwards then, like we said, you would simply integrate with respect to t. Okay. So all I'm going to do here then to begin with is differentiate this expression here with respect to t. So dx by dt here, that would give me the velocity, v. So we'll just go term by term here. So t cubed, if I differentiate that with respect to t, that would be 3t squared. We get 3t squared. Minus 4t squared, so that would be minus 4 times 2, so that's minus 8. Reduce the power by 1. So I get minus 8t there. And then finally minus 3t, that would give me minus 3 if we differentiate that with respect to t. And like we said then, this is when v equals 0. So the particle p is instantaneously at rest when v equals 0. So what I'm going to do now is set v here equal to 0. So 3t squared minus 8t minus 3 equals 0. So here we've got this quadratic equation that's equal to 0. So the first thing that we should do is just check whether this factorizes, and in this case it does factorize. So I can factorize this into double brackets here, where this will be equal to 0. So what we get here is 3t plus 1 and t minus 3. Okay. So from here we obtain two solutions for t. So I've got 3t plus 1 equals 0. So in that case then, we would get that t equals minus a third there. And we've got this solution here, which would be t equals 3. Okay, so t equals minus a third and t equals 3. However, we have a bit of an issue here because t is greater than or equal to 0. Okay, so in that case then, we need to omit this solution here. Okay, so we don't include that solution there. So t cannot equal minus 1 over 3 because t is only defined, or this equation here is only defined for t being greater than or equal to 0. Okay, so in that case then we know that t is equal to 3 here. So what I need to do now is take this value of t here and substitute that now into this equation here for the displacement. Okay, because what we're actually looking for here is the displacement of p when it is instantaneously at rest. So the particle p is instantaneously at rest when t equals 3. So now we're going to substitute t equals 3 into this equation here. So x is equal, so I've got t cubed, so that's 3 cubed. Got 3 cubed there. Minus 4t squared, so that's minus 4 lots of 3 squared. Minus 4 lots of 3 squared. Then we've got minus 3 lots of t, so that's minus 3 lots of 3. So if we evaluate this here, 3 cubed is 27. 3 squared is 9, so minus 4 times 9 is minus 36. And finally, minus 9 here. So what would I get here? Well, 27 minus 36, that's minus 9. Minus another 9 there, that gives me minus 18. Okay. So that's in meters, so that's minus 18 meters there. And obviously, don't worry about the fact that this is negative here, because we're talking about the displacement rather than the distance here. If this was the distance, then obviously we would need the absolute value, but because it's displacement, it can be negative. So, like I said, don't worry about the fact that it's negative. That's absolutely fine. In this case here, either way, you should get that you should obtain minus 18 meters there for the displacement of P when it is instantaneously at rest. And there we have it. So that's the solution there to question 1. So we just say, look now at one more question here, we have question 2 where we have a particle P that travels in a straight line such that its acceleration at time t seconds is given as 2t minus 8 meters per second squared. We're then told at time t equals 0, v is equal to 15 meters per second. So for the first part then, part A, we want to show that P is instantaneously at rest when t equals 3. So I see this phrase straight away that P is instantaneously at rest. So let's just highlight this here. So if the particle P is instantaneously at rest, we know that V, the velocity, is equal to 0. Let's just make a note of this here. So this is when V equals 0. Okay. So obviously we need the velocity here, but we start with the acceleration. Okay, we know the acceleration at time t seconds is given as 2t minus 8. So let me just make a note here. Displacement, velocity, and acceleration. So to go down here, for example, if you have the displacement and you want the velocity, you would need to differentiate with respect to t. So to go down then, you simply differentiate with respect to t, so d by dt. And then to go backwards here, so for example, if you have the acceleration, like we do here, and you want the velocity, then we need to integrate with respect to t. So that's the integral with respect to t. So because we start with the acceleration here and we want the velocity, like we said then, we need to integrate a here with respect to t. So v is equal to the integral of a with respect to t. So that's the integral then. Well, a is 2t minus 8. So 2t minus 8 here. And we integrate this then with respect to t. And this here is a nice straightforward integral to evaluate now. So add 1 to the power divided by the new power. So what I get here then is t squared. We get minus 8t here. And we have no limits on the integral, so don't forget the constant of integration. So we need plus c as well. Okay. Now we have these conditions here. So we know at time t equals 0, v is equal to 15 meters per second. So this is the velocity here, v. So when t equals 0, v is equal to 15. So all I'm going to do then is substitute 0 here for t, then set v here equal to 15, like we're told from these conditions here. So 0 squared minus 8 lots of 0, so minus 8 times 0, and then plus c. And this here is equal to v, which is 15 meters per second. So if we evaluate this here, 0 squared is 0, 8 times 0 is 0. So all we get then is that c equals 15. Okay. So now what I can do is rewrite my equation here for the velocity v. So therefore v, that's equal to t squared minus 8t plus c, where c is 15. Okay. So what we have now is the equation here for the velocity. Okay. So like we said then, P is instantaneously at rest when V equals 0. So what I'm going to do now is take this quadratic here for V and set that equal to 0. So t squared minus 8t plus 15 is equal to 0. Okay. And what I'm hoping I can do here then is factorize this, and we can in this case factorize. So what I get then is t minus 3 and t minus 5 here. And that's equal to 0. And what this gives us then is two solutions here for t, but all we're concerned about for part A then is showing that p is instantaneously at rest when t equals 3. So therefore we can solve here. So therefore t is equal to 3 as required. Okay. So that's what we need to do for part A. So like we've seen there, we've shown that p is instantaneously at rest when t equals 3. Okay. So that's part A done. So what about part B then? So part B says, hence or otherwise, find the other value of t for which p is instantaneously at rest. And that basically just follows on then from part A. So that's from the other solution here. So we saw, so we had t minus 3 and t minus 5 equals 0. So t minus 5 also equals 0 here. So this one here we've already solved. That gave us t equals 3. So t is equal to 3. Then we solve this one here then. T minus 5 equals 0. So therefore t must equal 5. So the other value of t for which p is instantaneously at rest is t equals 5. Okay, so part B done. Nice and straightforward. Now for part C then, it says calculate the distance between the 2 points at which p is instantaneously at rest. So what do we do here? There's a little bit more work involved here for part C. So what I'm going to do to begin with is just quickly clear the screen and then we can have a go at part C. So we just take a look then at part C here. Like we said, we just want to calculate the distance between the 2 points at which p is instantaneously at rest. We've just cleared the screen, but let's just recap those 2 points then. So from part A and B, the 2 points at which p is instantaneously at rest, well, we saw for part A then, that was t equals 3. So we've got t equals 3, and then the other point that we established in part B was t equals 5. Okay, so we've got t equals 3 and t equals 5. So all we want to do here is calculate the distance then between t equals 3 and t equals 5. So what we started here with was the acceleration. So we had a equals 2t minus 8. What we did then is we integrated to obtain the velocity. And now because we're talking about distance here, we actually need the displacement. Okay, so again, let's just make a note of this here. You've got the displacement, velocity, and acceleration. So to go down here, we differentiate with respect to t. So d by dt. And then to go up here, we integrate with respect to t. Okay. So we started with the acceleration. We integrated to obtain the velocity. So let's just recap here what the velocity was. That was t squared minus 8t plus 15. And now, like we said, we need the displacement here because we're looking at distance. Okay. So now, again, we need to integrate v here with respect to t. So for s then, the displacement, that is equal to the integral of v, the velocity, with respect to t. So that's going to be the integral then of t squared minus 8t plus 15. Got t squared minus 8t plus 15. So that is with respect to t. And if we think about this for a moment, if we're looking for the distance between these 2 points, I think a sketch here might help. If I quickly draw this underneath them, let's do it over here. That's my y-axis, and this is my x-axis here. Anyway, I quickly sketch this quadratic here, so t squared minus 8t plus 15. That would look, say, something like this here. Obviously, we'll cut through at 15, but if I just quickly draw it so it looks like this here. If I say that that is t equals 3, and this here is t equals 5, then what we're looking for then is the distance here underneath the curve, okay, or underneath the x-axis here. So we're looking for this region here, okay? And this region here would be the distance then between these 2 points at which P is instantaneously at rest. Now what you should obviously expect here is this value, this integral here between 3 and 5, you would expect that to be negative, okay, because it's underneath the x-axis. But obviously because we're talking about distance here, that can't be negative, so we're going to take the absolute value at the very end. So all we need to do then is evaluate this integral here with these limits. So pretty standard, pretty straightforward. Let's evaluate this here then. So add 1 to the power, divide by the new power. So I'm going to get t cubed over 3. Like we get t cubed over 3. I then got minus 8t, so add 1 to the power, divide by the new power. So I'm going to get minus 8t squared over 2. So that's minus 4t squared. And then finally, we've got 15 here, so that would be plus 15t. And this is between 3 and 5. Okay. So all I need to do now is substitute these values in here of 5 and 3. Okay. So we start by substituting 5 in then. I'm going to get 5 cubed over 3, so that's 125 over 3. I've got minus 4t squared, so that's minus 4 lots of 5 squared. So 5 squared is 25, times that by 4 here, so that would be 100, so minus 100. And we've got 15 lots of 5, so that would be plus 75 there. We'll put a bracket around that, just so we don't confuse ourselves. And we subtract here the lower limit here, so 3 cubed is 27 over 3, so that's 9. Minus 4 lots of 3 squared, so that's minus 36. And then 15 times 3, so that's going to be plus 45 there. Okay. So all you need to do here then is put all of this into your calculator. And if you evaluate this correctly, what you should get then is minus 4 over 3. Okay. So what we've obtained here is a negative value. But like we said, that was expected because the area here that we're looking to find, well, that's underneath the x-axis when we integrate. So that would be negative. So like we expected, we got a negative value. But because we're talking about distance here, so we're talking about distance, then that must be positive. So all we do here is we take the absolute value. So distance is positive. So distance is positive. So therefore, the distance between the 2 points at which P is instantaneously at rest is positive 4 over 3. Okay, so therefore, distance is equal to 4 over 3 there. Okay, and there we have it. So that's the solution to part C, and that gives us the solution there to the very last question. And that actually brings the end of this video on exam revision for variable acceleration.